The Second World War was not won by armies alone. It was won by the ability to build faster than the enemy could destroy. Guns, tanks, ships, and aircraft mattered, but behind each stood an even greater weapon, the assembly line. America's mastery of mass production turned factories into arsenals and workers into an industrial army. It was not genius or luck that overwhelmed the Axis, it was output. When war erupted in 1939, American industry was still recovering from depression. Within 2 years, it was transformed into the largest manufacturing system the world had ever seen. President Roosevelt's call to become the arsenal of democracy set the tone. Civilian car factories converted to tank and aircraft plants. Typewriter companies built machine guns. Refrigerator lines began stamping bomb casings. The country's industrial geography changed overnight. Detroit became the motor pool of war. Los Angeles became the heart of aviation. Pittsburgh poured steel for the world. The key to this transformation was standardization. Engineers designed machines, parts, and tools that could be mass-produced with interchangeable components. Each piece fit into every machine of its kind. The same principle that once made automobiles affordable now made tanks replaceable, rifles repairable, and aircraft buildable in the thousands. Production no longer depended on artisans but on systems. Factories became synchronized units of an industrial organism. Scale followed design. The Ford Motor Company's Willow Run plant built B-24 bombers using automotive methods. A bomber that once took 200 days to assemble could now be built in under 20. The plant stretched more than a mile, employing 40,000 workers and producing one bomber every hour at its peak. In shipyards, prefabricated sections of Liberty ships were welded together like toys. Airplane factories turned out thousands of fighters a month. This acceleration was powered by the integration of labor, machinery, and management. Workers were trained for narrow tasks. Machines repeated them endlessly. The human hand guided the machine guided the schedule, and the schedule guided the war. Women filled the factories as millions of men fought abroad. The image of Rosie the Riveter captured the spirit of total mobilization, an economy where every motion had purpose and every product was a bullet, a plane or a ration for victory. The industrial rhythm was relentless. Production lines operated 24 hours a day, 7 days a week. Government agencies coordinated materials, logistics, and wages. The War Production Board rationed steel, copper, and rubber. Engineers redesigned vehicles and weapons not for elegance but for speed of manufacture. Tanks lost ornamental features. Aircraft frames were simplified for quick assembly. Every design decision became a question of minutes saved and units produced. Efficiency itself became strategy. Numbers tell the story. By 1944, the United States was producing nearly half of all war materiel in the world. Over 300,000 aircraft, 100,000 tanks, and more than 2,000 warships were built within 4 years. What took other nations months to replace, America replaced weekly. Production outpaced destruction. It was not simply industrial power, it was industrial momentum, an unstoppable flow of material that buried the enemy under tonnage. But mass production was more than output. It was adaptation. Every new front brought new requirements. Desert filters for Africa, cold weather engines for Europe, reinforced hulls for the Pacific. Engineers redesigned machines faster than the enemy could learn from them. The same system that built automobiles now built evolution itself. Factories became laboratories where design met necessity in real time. The cost was discipline and fatigue. Workers endured endless shifts. Managers faced impossible quotas. Accidents, shortages, and strikes tested the system, but it never stopped. It could not stop. The industrial engine had become as vital as any battlefield. Generals measured victories not just in miles gained, but in machines delivered. When the war ended, the assembly lines that had built weapons began building peace. The same factories that produced bombers produced civilian airliners. Tank plants built tractors. The science of interchangeable parts and continuous flow became the foundation of modern industry. Mass production had proven that speed, organization, and volume could win wars. It was the invisible front, where machines built machines, and where victory was measured not in courage or strategy, but in output per hour. The industrial army of the home front never fired a shot, but it fired the world's greatest barrage of productivity. And in doing so, it redefined power, not as possession, but as production. Mass production during the war became a new form of warfare, one fought in factories, not trenches. Every assembly line was a front, Every worker a soldier of steel and precision. The system's strength lay in repetition. A single perfected process could be multiplied across hundreds of plants. That meant thousands of identical engines, tens of thousands of rifles, and millions of rounds of ammunition flowing from one synchronized industrial organism. The United States had learned this logic decades earlier from Henry Ford's Model T assembly line. Now it was applied to everything from fighter planes to field rations. The goal was not craftsmanship but consistency. Engineers simplified designs, eliminating any part that slowed production. Welds replaced rivets. Bolts were standardized across vehicles and weapons. A mechanic in France could repair a tank built in Michigan using the same wrench as one repairing a truck in the Philippines. It was the standardization of the entire war. Factories learned to treat metal as material, not art. Components were stamped, pressed, and welded with mechanical rhythm. Conveyor belts carried unfinished planes past teams of workers, each performing one motion, then another, until an aircraft rolled out complete. The difference between war in 1914 and war in 1944 was not only technological, it was procedural. The machine had absorbed the craftsman. Training became industrial too. The U.S. government opened technical schools to train millions of workers in welding, machining, and assembly. Women filled those ranks in unprecedented numbers, running lathes and cranes with the same discipline once expected of soldiers. Posters and radio broadcasts turned factory labor into patriotic duty. Every rivet was a bullet, every finished engine another victory. The home front became the supply artery of the front line. Logistics matched production in complexity. Materials moved through rail networks, barges, and trucks in a constant loop. Steel from Pittsburgh became aircraft frames in California, ammunition in Illinois, and tanks in Detroit. Rubber, copper, and aluminum were rationed by government committees that functioned like military staffs. Nothing was wasted, nothing stood still. It was economy as mobilization, society as machinery. The results dwarfed imagination. Between 1942 and 1945, American shipyards launched more tonnage than all the Axis powers combined. Aircraft factories produced so many bombers that airfields had to expand just to store them. Tank assembly lines poured out armor faster than crews could be trained to drive it. The numbers were not just high, they were exponential. Production scaled with experience, efficiency feeding on itself until output became overwhelming. This overwhelming capacity forced strategic change. The Allies could fight prolonged campaigns because losses could be replaced instantly. A destroyed bomber squadron was rebuilt in weeks. Tanks lost in North Africa reappeared in Italy. Every setback on the battlefield was absorbed by the factory system behind it. Industrial resilience became military endurance, yet this system came at a cost. It demanded discipline bordering on regimentation. Workers labored long hours under fluorescent light, performing repetitive tasks without pause. The human body became another machine in the chain. Morale was maintained by propaganda, incentives, and the shared belief that production was survival. In that sense, the factory was both forge and front line, a place where patriotism met exhaustion. By 1945, the model had proven unassailable. America's wartime output exceeded that of Germany, Japan, and Italy combined. Industrial power had replaced manpower as the decisive element of warfare. The modern world's balance of power would forever rest not on armies in the field, but on factories at home. When the war drew to a close, mass production had not only won battles, it had rewritten the structure of civilization. The same methods that once built rifles and bombers now shaped the post-war world, defining everything from transportation to communication. The techniques of repetition, efficiency, and interchangeable design had become the new grammar of industry. America had proved that victory could be engineered. The home front's industrial mobilization had done more than supply armies. It had created a model for national organization. Every sector of society had been synchronized. Universities trained engineers for production. Scientists designed materials to fit factory needs. Government agencies managed resources with military precision. Even culture adapted. Radio programs, posters, and films all echoed the rhythm of the assembly line, teaching citizens that unity meant productivity. The war had mechanized not just labor, but belief. Factories that once turned out bombers began building civilian aircraft, cars, and appliances. The transition was seamless because the principle was the same: modular design, continuous flow, and standardized components. What had powered total war now powered total modernization. In a few years, industrial mass production created a new middle class. flooded markets with affordable goods, and transformed consumer expectation. The peacetime abundance of the late 1940s and 50s was the shadow of wartime mobilization. The military, too, never abandoned the system. The lessons of rapid scaling, supply coordination, and interchangeable design became permanent elements of defense strategy. The Cold War would depend as much on industrial potential as on nuclear arsenals. The concept of readiness itself came to mean the ability to produce quickly, in volume, and with precision. From aircraft carriers to missiles, mass production remained the heartbeat of military power. Culturally, it changed how people imagined war. The heroic image of the lone soldier gave way to the anonymous laborer, the unseen worker whose repetitive task built victory. The collective replaced the individual. Success was measured not in valor but in output. The idea that organization could defeat chaos, that structure could substitute for genius, became the modern creed. Yet the triumph was not without consequence. The same system that had given humanity control over production also distanced it from creation. Machines and processes began to define pace and purpose. People adapted to the rhythm of the assembly line, their work measured in speed and volume rather than craft. Efficiency became both virtue and burden. In historical terms, the war had industrialized modernity itself. It had proven that nations could convert abstract plans into material reality at astonishing speed, that will and machinery could merge into a single force. Factories had replaced fortresses. Blueprints had become as important as battle plans. The front line was no longer at the edge of an empire. It was wherever production began. By 1945, the lesson was clear. Control of production meant control of destiny. The Axis powers had fought with courage and strategy, but they had fought against an engine too vast to exhaust. Mass production had turned geography, manpower, and time into variables that could be managed by design. It was the first modern proof that power was not what a nation possessed. It was what a nation could make. The war ended, but the assembly line never stopped. Its sound became the hum of peace, the rhythm of cities, the heartbeat of progress. From tanks to tractors, bombers to airliners, the principle was the same. Repetition builds power, and power builds history. When war began, Britain was starving. German U-boats hunted Allied convoys across the Atlantic, sinking ships faster than they could be built. Food, fuel, and weapons never reached their destinations. The solution would not come from new weapons or tactics, but from industrial engineering on an unprecedented scale, ships that could be built faster than the enemy could destroy them. They were called Liberty ships, and they changed the economics of war. Before 1941, shipbuilding was slow and artisanal. Each vessel took nearly a year to construct, crafted by skilled shipwrights using riveted steel plates. America's challenge was to turn this craft into a factory process. Under the U.S. Maritime Commission, and driven by industrialist Henry J. Kaiser, the United States built a new kind of shipyard, one based on assembly lines, prefabrication, and unskilled labor. Sections of ships were welded rather than riveted, assembled in parallel, and joined like pieces of a machine. The first Liberty ships were modest, 441-foot cargo vessels designed to carry about 10,000 tons. Their design emphasized simplicity over beauty. They were slow, noisy, and unglamorous, but they could carry everything: tanks, planes, ammunition, grain, even entire locomotives. Each ship was identical, allowing interchangeable parts and rapid assembly. For the first time in history, ships were built like cars. The results were astonishing. In 1941, a Liberty ship took about 230 days to build. By 1943, that time had fallen to less than 45 days. The record was set by the Robert E. Peary, assembled in just 4 days, 15 hours, and 29 minutes. Shipyards worked around the clock, employing hundreds of thousands of men and women, many of whom had never worked near the sea before. Welders, steel cutters, and crane operators replaced traditional craftsmen. The shipyards themselves became models of wartime efficiency, combining engineering precision with industrial speed. The Liberty ship program became a logistical miracle. Over 2,700 were built during the war, more tonnage than all Axis powers combined could sink in a year. They formed the backbone of Allied supply, carrying 75% of all cargo across the Atlantic and Pacific. Every major campaign, from North Africa to Normandy, relied on their cargo holds. When the Red Army advanced westward, it was Liberty ships that delivered American food, trucks, and fuel through the Arctic convoys to Murmansk. They were not perfect. Welded hulls occasionally cracked in cold seas, earning them the grim nickname Kaiser's coffins. Yet their losses were acceptable compared to their output. Each Liberty ship cost less than $2 million, cheap enough that replacing one was faster than repairing it. Their very disposability became their strength. By 1945, Liberty ships symbolized the industrial power that defined America's role in the war. They demonstrated that mass production could defeat scarcity, that speed could outweigh precision, and that logistics could win where weapons could not. When the war ended, hundreds of them continued to sail for decades, rebuilt, sold, or converted into civilian cargo ships. Some became hospitals, training vessels, and floating warehouses. The Liberty ship was more than steel and rivets. It was the embodiment of an idea, that a nation could outbuild its enemies, that the line between factory and battlefield could vanish, and that victory could come from the discipline of production. They were not elegant, but they were unstoppable. The ships that fed the world, armed the Allies, and turned industry itself into a weapon. The scale of Liberty ship production changed not only the war, but the nature of industry itself. America's shipyards became the largest construction effort in human history. New yards appeared on both coasts: Richmond, California, Portland, Oregon, Baltimore, Maryland, and Brunswick, Georgia. Each operated like an immense assembly line, welding prefabricated sections together under the glow of floodlights that never dimmed. Kaiser's philosophy was simple: build them faster than they can sink them. Workers came from everywhere. Housewives, farmers, and teachers were trained to weld and rivet. Rosie the Riveter became the symbol of a workforce that was nearly half female. Skilled trades were no longer the bottleneck. Process was. Pre-assembled modules, keels, decks, bulkheads, engine rooms were built in parallel and then joined together in final assembly. Cranes moved entire sections into place in minutes instead of days. Where once a shipyard launched a handful of vessels per year, Liberty yards launched several each week. Training centers taught tens of thousands of welders and engineers the new techniques. Welding replaced riveting because it was faster and cheaper, but it required careful discipline. Faulty welds could crack under stress, and cold weather sometimes split hulls mid-voyage. Engineers solved the problem by redesigning joints, improving steel quality, and reinforcing the hulls with external plates. Failures were studied and corrected within weeks. The industrial feedback loop was as relentless as combat itself. The ships carried everything a global war demanded. Grain, gasoline, ammunition, tanks, aircraft, and medical supplies filled their holds. Convoys of Liberty ships stretched across the oceans, escorted by destroyers and corvettes. They brought supplies to Britain when U-boats threatened starvation, delivered equipment to the Soviet Union through Arctic convoys, and carried reinforcements to the Pacific Islands. Each vessel's capacity, 10,000 tons, meant that a single convoy of 50 ships could equip an entire army division overseas. Their importance reached beyond logistics. The Liberty ship program unified labor, science, and management into a single wartime machine. It demonstrated how government coordination and private industry could achieve miracles under pressure. The U.S. Maritime Commission oversaw design and procurement, while Kaiser managed deadlines with ruthless efficiency. Bonuses were paid for speed, penalties for delay. Propaganda celebrated each launch as a victory. Crowds gathered as ship after ship slid into the water under banners reading, "Full speed ahead for freedom." For the sailors who crewed them, Liberty ships were both lifelines and prisons. They were slow, barely 11 knots, and vulnerable, but they carried the world's hopes on their steel decks. Crews braved torpedoes, storms, and isolation. The vessels lacked luxury. Accommodations were sparse, the noise constant, and the risk omnipresent. Yet morale remained high because every sailor understood the scale of what they served. A floating artery feeding the armies of liberation. By late 1944, Liberty ship production had reached its peak. Newer victory ships were faster and more durable, but the Liberty remained the workhorse. It had already done its job, overwhelming the enemy through numbers, sustaining allies through endurance, and proving that engineering could win wars as surely as weapons. When Roosevelt called America the arsenal of democracy, the Liberty ship was its clearest proof, a vessel born not of design perfection but of national resolve. When the war ended, the Liberty ship remained a monument to industrial power. More than 2,700 had been built, an achievement that dwarfed every previous shipbuilding effort in history. Many of them continued to serve long after 1945. Hundreds were sold to private companies, converted into freighters, hospital ships, and troop transports. Others became floating warehouses, training ships, or civilian cargo carriers in the rebuilding of Europe and Asia. They hauled grain for the Marshall Plan, transported refugees and carried coal, food, and machinery to shattered cities. Their legacy was practical as well as symbolic. The techniques pioneered in their construction, modular design, prefabrication, and assembly line production, became the blueprint for post-war industry. Shipyards that had once been temporary wartime projects evolved into permanent industrial centers. Welding replaced riveting everywhere. Large-scale manufacturing learned from Liberty Ship logistics. Build simple standard units in massive numbers, and let speed replace perfection. The idea spread beyond shipbuilding, influencing aviation, construction, and even computing. In strategic hindsight, Liberty ships were not glamorous weapons, but they were indispensable. Without them, every victory, El Alamein, Normandy, the Pacific Island campaigns, would have stalled for lack of fuel, ammunition, or food. The war's decisive battles were won by men on the front lines, but they were supplied by these slow, grey freighters. A single Liberty ship carried enough fuel to fly a bomber wing for a week, or enough rations to feed an army division for a month. The logistics they enabled turned tactical victories into strategic momentum. The cost was never forgotten. Hundreds of Liberty ships were sunk by submarines, mines, and aircraft. Thousands of merchant sailors lost their lives in the cold seas of the Atlantic and Arctic. Their sacrifice was as crucial as any soldier's. Each ship launched was a gamble against time and danger. One more vessel to bridge the ocean faster than the enemy could destroy it. As the Cold War dawned, the remaining Liberty ships formed the backbone of the U.S. Merchant Reserve Fleet. They were refitted, modernized, and held in readiness for future crises. Some served again during the Korean War, transporting men and materials to another distant conflict. Others lay quietly at anchor, symbols of a different kind of courage, the patience and persistence of production. 2 Liberty ships still sail today as museum vessels. The SS Jeremiah O'Brien in San Francisco and the SS John W. Brown in Baltimore. Their riveted decks and humming engines stand as living artifacts of an age when industry became strategy. Visitors walking their corridors see not luxury but discipline, steel, function, and speed. The Liberty ship embodied a nation's philosophy, that victory could be built, not just fought for. It was proof that the assembly line could be as powerful as the assembly of armies. Every plate welded, every section lifted, and every ship launched carried the same message. That mass production, guided by purpose, could move the world. They were the ships that fed empires, bridged oceans, and outpaced destruction. They were not built to last forever, only long enough to win. And they did. When American bombers took flight over Europe, their power depended not just on altitude or payload, but on precision. Dropping bombs from 20,000 feet was like throwing stones in a hurricane. Wind, speed, and gravity turned every strike into a guess. The U.S. military needed a way to turn chaos into calculation, to make bombing a science instead of an art. The answer came in the form of an optical machine, so advanced it was once described as the secret weapon of victory. It was the Norden, Bombsight, the mechanical brain that promised to make every bomb fall true. Developed by Dutch engineer Carl Norden, a devout and methodical man, the Bombsight began as a peacetime invention. In the 1930s, the U.S. Army Air Corps adopted it for high-altitude daylight bombing. Inside its compact steel casing was a gyroscopically stabilized analog computer. The bombardier would enter altitude, airspeed, and wind direction. The device then calculated the precise release point. Through its sight, the bombardier tracked the target, and the Norden automatically adjusted the bomber's course. It was both telescope and computer, part optics, part mechanism, and entirely revolutionary. The Norden was treated with near-religious secrecy. Every bomb site was guarded, locked under armed watch when not in use. Bombardiers took an oath to protect its secrets, and in the event of a crash, they were instructed to destroy it with a pistol or grenade. The United States believed it held a device that could deliver surgical precision, bombs through a pickle barrel from 20,000 feet, as propaganda boasted. While that phrase was optimistic, the Norden did represent a leap forward in aerial targeting. Inside a bomber, the Bombsight became the command center of the mission. During a run, the The pilot turned control over to the bombardier, who steered the plane using the Norden's linked autopilot system. Through the eyepiece, he saw the world shrink into crosshairs, bridges, rail yards, and factories, targets reduced to geometry. As he stabilized the image and the system completed its calculations, a small motor automatically released the bombs. The process lasted only seconds but determined the outcome of entire campaigns. In practice, precision was elusive. Weather, flak, enemy fighters, and human stress all affected accuracy. Over Europe, bombs rarely landed exactly where planned. Yet compared to earlier systems, the Norden was unmatched. Its accuracy improved circular error from thousands of feet to hundreds, allowing concentrated strikes on strategic targets. Entire industrial centers, ball-bearing plants, oil refineries, and transport hubs could now be targeted systematically. The Norden did not make bombing perfect, but it made it scientific. The device's complexity was astonishing. More than 2,000 components, gears, cams, gyroscopes, prisms, and servo motors, worked together in harmony. Each bombsight took weeks to build and calibrate. Norden's team and later the Victor Adding Machine Company produced tens of thousands during the war, each costing about $10,000, nearly as much as a fighter plane. Despite its delicacy, it endured vibration, cold, and the brutal conditions of combat flight. It was a masterpiece of mechanical engineering in an age before digital logic. The Norden's greatest triumphs came during the U.S. daylight bombing campaigns of 1943 to 1945. Flying fortresses and liberators carried it over Germany, striking oil depots and transportation lines that crippled the Nazi war machine. In the Pacific, it guided attacks on Japanese shipyards and cities. It was also used on the Enola Gay, the B-29, that dropped the atomic bomb on Hiroshima, linking the Norden indirectly to both the technological zenith and moral weight of the air war. But the Norden bombsight was more than a tool of destruction. It represented a mindset. It symbolized faith in calculation, in the belief that engineering could make war rational. It turned bombardiers into technicians, pilots into instruments of precision. Its smooth gears and spinning gyroscopes mirrored a nation convinced that science could control even the chaos of battle. After the war, newer electronic systems and radar-guided bombs rendered it obsolete. But its legacy lived on in every guidance computer that followed. The Norden was the ancestor of precision warfare, the moment when human judgment first fused with mechanical computation. It did not always deliver perfect accuracy, but it changed what accuracy meant. In the cold air above Europe, men peered through its lenses and believed they were seeing the future. A future where mathematics could aim, machines could think, and war itself could be reduced to numbers. The Norden bombsight transformed bombing from instinct to engineering. Yet its story was not only about technology, it was about belief. The United States Army Air Forces built an entire doctrine around the Norden's promise of precision. It was the core of daylight strategic bombing, the idea that wars could be won by destroying the enemy's industrial heart from the air, without the need for costly ground invasions. In theory, the Norden made this possible. American planners envisioned fleets of B-17s and B-24s flying in tight formations, striking factories, bridges, and oil refineries with surgical accuracy. Precision daylight bombing became both strategy and propaganda. The bombsight was its talisman, the instrument that made moral warfare conceivable. If bombing could be precise, it could also be justifiable. In practice, reality was harsher. Clouds, anti-aircraft fire, wind drift, and pilot fatigue all conspired against accuracy. Even with the Norden, only about 20% of bombs landed within 1,000 feet of their targets. Still, the device gave commanders something no other air force possessed: confidence in the possibility of precision. The British, after suffering heavy losses in early raids, turned to nighttime area bombing, blanketing cities to crush morale. The Americans, armed with the Norden, insisted on daylight attacks aimed at specific industries. This division of philosophy shaped the Allied air war. The Norden became more than a tool. It was the hinge between two different kinds of war: destruction by calculation versus destruction by saturation. Technically, the bombsight's genius lay in its stabilizing gyroscope and analog computing system. It corrected for aircraft pitch, roll, and speed, continuously updating the angle of attack as the bombardier tracked the target. Its interface, a set of knobs, dials, and crosshairs, was intuitive enough to operate under stress, but complex enough to demand months of training. A single mistake in calibration could send bombs miles off course, so bombardiers were treated as elite technicians, sworn to secrecy and precision. They wore sidearms, not for combat, but to protect or destroy their equipment if captured. Manufacturing the Norden required microscopic precision. Each site was hand-assembled in clean rooms by technicians trained like watchmakers. Calibration took days. Testing took weeks. The resulting machine looked almost delicate, but in flight it endured vibration, freezing air, and the shock of bomb release. It became a symbol of mechanical discipline, the idea that reliability could be engineered, not improvised. As bombing campaigns intensified, the Norden's limits became clearer. Weather over Europe often obscured targets. Smoke from previous raids blinded optics. Turbulence disrupted calculations. Engineers responded by integrating radar and improved autopilot systems. The Norden remained the heart of the process, but now worked as part of a larger electronic ecosystem, the beginning of modern integrated targeting systems. By 1945, it had evolved from a single bombsight into an entire philosophy of warfare. It gave birth to an industry that believed in precision as destiny, that machines could remove uncertainty from war. Even when its accuracy fell short, its influence endured. It changed how nations built, planned, and justified aerial power. The Norden bombsight was both a marvel and a myth, a promise of perfect accuracy in an imperfect world. It taught engineers to chase precision beyond the limits of weather, fear, and chaos. And in doing so, it laid the intellectual groundwork for everything that followed. Guided missiles, laser targeting, and the digital navigation systems that would someday make its spinning gyroscopes obsolete. The Norden bombsight's legacy was measured not just in missions flown, but in the transformation of how nations conceived warfare itself. Before it, bombing was guesswork. After it, bombing became data. The Norden had fused mathematics, optics, and human judgment into a single instrument, the prototype of modern machine-assisted warfare. Its influence stretched far beyond the skies of the 1940s, shaping technology, ethics, and the philosophy of control in the atomic age that followed. When the Allied air campaign reached its peak in 1944, thousands of bombers carried the Norden into battle every day. Each bombardier's compartment became a miniature observatory, glass, steel, and spinning gyroscopes guiding destruction with scientific detachment. Over Germany, oil refineries, ball-bearing factories, and rail hubs were struck with unprecedented consistency. Though the precision was never perfect, the sustained pressure shattered production lines and paralyzed the enemy's mobility. The bombsight had become a weapon of attrition by calculation, multiplying the effectiveness of each sortie through organization and measurement. In the Pacific, it played a different role. The vast distances and unpredictable weather made traditional navigation nearly impossible. The Norden allowed long-range bombers like the B-29 to aim through cloud and turbulence, relying on optical stabilization and integrated autopilot. Its use on the Enola Gay over Hiroshima and later the Boxcar over Nagasaki gave it a grim immortality. The device that was meant to make bombing humane became the instrument that delivered the most destructive weapons ever built. Precision, once a moral argument, now carried the weight of apocalypse. After the war, the bombsight became a victim of its own success. Radar, electronic navigation, and digital computation quickly surpassed its mechanical limits. But engineers who had mastered the Norden's delicate synchronization of gears and gyros carried their expertise into new fields. The same principles guided early analog computers, fire control systems, and missile guidance units. The lineage from Norden's hand-cranked mechanisms to the first digital targeting computers was direct and unmistakable. Culturally, the bombsight came to symbolize both the promise and the peril of scientific warfare. It embodied faith in control, the belief that human reason could manage destruction with precision. Yet the devastation of Dresden, Tokyo, Hiroshima, and Nagasaki exposed the illusion of clean war. The Norden had narrowed the margin of error, but not the moral distance between calculation and consequence. Its crosshairs, once symbols of mastery, now looked like questions. By the 1950s, most Norden sites were decommissioned, stored, or sold as surplus. A few found their way into museums, silent relics of a mechanical age that believed perfection could be built with gears. Yet every modern guidance system, from cruise missiles to GPS bombs, carries its DNA. The gyroscopic stabilization, predictive computation, and automation that defined the Norden remain the foundation of precision warfare. Carl Norden himself never saw his invention as a weapon. A quiet engineer, he considered it a tool for minimizing civilian casualties, not maximizing efficiency. He died believing he had made war more humane. History, however, gave his creation a more complex verdict. The Norden bombsight had not made war precise. It had made precision an ideal, one that the world would forever pursue, never fully reach. In the cold air above Europe, the hum of gyroscopes and the turning of gears marked the beginning of a new age. An age where machines could measure the unmeasurable, where every decision could be computed, and where the illusion of control became as powerful as control itself. The Norden bombsight was not merely an instrument of aim, it was the first mechanical vision of total certainty, and the moment humanity learned that even perfect aim cannot guarantee a just target. Allied victory depended on supply lines. When natural resources were cut off, chemistry provided substitutes. In the early years of the war, Japan seized most of the world's natural rubber. The loss threatened tires, gaskets, and many vehicle components. Synthetic rubber and high-octane fuel became strategic necessities. American chemists and engineers turned raw science into mass production. The problem was twofold. First, chemists had to create polymers that matched the elasticity and durability of natural rubber. Second, factories had to be retooled to produce those polymers at scale. Researchers built on pre-war advances in polymer chemistry. They optimized monomer mixes, improved catalysts, and developed continuous polymerization processes that kept product quality stable over long production runs. Production lines moved from lab benches to giant mixers and extruders. Quality control measures measured tensile strength, heat resistance, and aging. Tires and hose makers adjusted formulations to accommodate the new materials. Fuel presented a parallel challenge. Aircraft performance depended on high-octane aviation gasoline. Lower octane reduced engine power and increased the risk of detonation. American refiners developed catalytic cracking and blending techniques to boost octane. They substituted scarce aromatics with synthetics and designed additives that suppressed knocking. Engineers also improved storage and transport to preserve fuel quality across long supply lines. These chemical solutions required coordination between government, academia, and industry. The War Production Board prioritized feedstocks and allocated scarce metals and fuels to synthetic plants. Universities supplied process research. Major corporations converted textile and chemical plants into polymer factories. Licensing and technical data flowed rapidly. Patents were subordinated to wartime needs. The wartime ethic replaced competition with collaboration. The scale of production was unprecedented. Synthetic rubber plants produced hundreds of thousands of tons per year. Refinery expansions and new cracking units multiplied high-octane output. The raw materials included petroleum, coal-derived gases, and chemical intermediates. Supply chains for basic chemicals, like benzene and butadiene, were secured and expanded. Trains and tank farms moved feedstocks to plants, and tankers carried finished fuel worldwide. The logistic network itself became part of the technological achievement. On the battlefield, the effects were tangible. Trucks ran on synthetic tires without catastrophic failures. Aircraft performed at designed power levels and completed missions that would have been impossible with lower quality fuel. The standardization of materials simplified maintenance. Field repair units learned the new characteristics of synthetic compounds and adapted procedures. Replacement parts arrived on schedule because the industrial base could supply them. Limitations existed. Early synthetic rubber had different aging and wear profiles. Some products cracked in extreme cold, others were more prone to heat buildup. Engineers refined polymer blends to address these weaknesses. Fuel additives required careful dosing. Incorrect blends could damage engines. The rapid pace of production sometimes produced quality variation. But feedback loops from the front allowed engineers to correct formulations in weeks rather than years. The strategic consequence was decisive. Where resource shortages might have grounded fleets or immobilized armies, synthetic chemistry kept machines moving. Chemical substitution converted shortages into manageable engineering problems. The Allied ability to field motorized formations airborne operations, and long-range air campaigns traced directly to these industrial chemical solutions. After the war, the techniques and plants did not vanish. The synthetic rubber industry matured into a peacetime sector. Refinery technology advanced civilian fuels and plastics. The wartime marriage of chemistry, engineering, and logistics became a model for future industrial mobilization. In the context of the war, synthetic rubber and fuel were not glamorous innovations. They were workhorse technologies. They proved that chemistry, when organized at national scale, could replace geography as a constraint on power. Synthetic chemistry's true strength during the war was its adaptability. Every shortage became a challenge of conversion. Natural rubber, once drawn from plantations in Southeast Asia, was replaced by polymers built from oil and gas. Every automobile, tank, and aircraft tire rolling through mud or snow carried the signature of chemical substitution. The synthetic rubber program began in earnest in 1942, when Japanese expansion severed Allied access to more than 90% of natural supplies. The United States launched the government rubber program, bringing together the major chemical companies: DuPont, Goodyear, Standard Oil, Firestone, and Goodrich. Rival firms that had once guarded patents now shared data and equipment. Within months, they built more than 50 new factories across the continent. Each plant produced one type of polymer: styrene butadiene for tires, neoprene for industrial seals, nitrile for fuel-resistant gaskets. The government financed construction, allocated raw materials, and coordinated transport. Industry supplied labor, machinery, and scientific expertise. By 1944, synthetic rubber output had surpassed 800,000 tons per year, completely replacing natural imports. Tank convoys, jeeps, and bombers relied on it. Allied logistics operated on a foundation of chemistry. Tires no longer depended on plantations or shipping lanes. Instead, they emerged from pipelines and reactors, proof that industrial networks could outpace geography. Fuel chemistry advanced in parallel. The introduction of catalytic cracking and alkylation transformed aviation performance. These refining processes, accelerated by wartime necessity, produced gasoline with octane ratings above 100. That single leap in chemistry increased aircraft power, range, and reliability. Fighters climbed faster and bombers carried heavier loads. Engineers learned that chemistry could multiply the effectiveness of machinery without redesigning the machinery itself. Synthetic lubricants and hydraulic fluids followed. They resisted freezing at high altitude and thinning under heat. Jet engines and long-range bombers benefited directly. The cumulative result was not spectacular like a new weapon, but pervasive, a quiet enhancement across every system. Chemical plants became part of the war's infrastructure of endurance. Where other industries built things to destroy, chemistry built materials to survive. Synthetic fuel and rubber were invisible to soldiers, but without them, the machines of war would have stalled in the mud. Their development required coordination on a continental scale: railroads feeding refineries, refineries feeding reactors, reactors feeding factories. By the war's end, the Allied ability to sustain mechanized warfare anywhere on Earth was no longer tied to resource luck, but to chemical knowledge. Synthetic production had replaced colonial dependency. The war proved that control of molecules could equal control of continents. It marked the point where chemistry ceased to be an auxiliary science and became an engine of strategy. The triumph of synthetic chemistry during the war was not a single invention but a transformation of scale. By the final year, the chemical industry had become a second army, quiet, invisible, and continuous. It fought through laboratories, pipelines, and furnaces instead of trenches. Every convoy, air raid, and mechanized advance relied on it. The war had begun with shortages and ended with surpluses, because chemistry had turned scarcity into a solvable equation. Synthetic rubber was the clearest proof of this transformation. Its production had surpassed 1 million tons annually by 1945, feeding every front. Engineers no longer worried about losing supply lines from Southeast Asia. Tire factories ran day and night, blending polymers with carbon black and new stabilizers to create compounds that outlasted their natural counterparts. Each formulation, some softer for transport, others harder for armor vehicles, was designed with mathematical precision. Laboratory control, not geography, determined the pace of movement. Fuel chemistry carried the same logic into the air. Catalytic refineries and alkylation plants delivered a steady flow of high-octane aviation gasoline. Each barrel represented the work of thousands, chemical engineers adjusting temperatures by degrees, operators balancing reactions, and inspectors ensuring purity to the last molecule. The result was flight reliability. Engines burned hotter and cleaner. Fighters and bombers that once struggled for range or altitude now exceeded both. The chemistry of octane had become a weapon of endurance. These synthetic processes reshaped labor and knowledge as well. Chemists became strategists. Universities trained thousands of engineers in polymer and petrochemical design. Wartime laboratories, at DuPont, Standard Oil, and the Bureau of Mines, formed the core of the post-war plastics and energy industries. The same catalytic beds that produced aviation fuel would later generate the polymers of the consumer age: nylon, polyethylene, and polystyrene. The war had forced chemistry into full maturity. On the front lines, the effects were rarely visible, but always felt. Tires resisted tropical heat and Arctic cold. Fuel stored for months remained stable. Mechanical failures dropped, and mobility increased. Commanders could plan campaigns without fearing resource collapse. Synthetic rubber and fuel had transformed logistics from vulnerability to weapon. They did not destroy the enemy. They simply ensured that nothing the enemy did could stop the machinery that would. After 1945, the chemical empire built in wartime became the foundation of modern civilization. Synthetic materials filled every home, laboratory, and factory. The same plants that had supplied armies now supplied economies. In the long arc of history, the synthetic rubber and fuel program marked the moment humanity learned to manufacture nature itself. It was chemistry's quiet victory, unseen in battle, but decisive in outcome. The war had proven that equations could replace empires, and that the mastery of matter was the surest route to power. Wars are fought with weapons, but they are won with information. Beneath the noise of battle, a quieter war unfolded, one of ciphers, mathematics, and machines. It was a war where silence meant victory and secrecy meant survival. The Second World War became the first conflict where intelligence was mechanized, where human logic merged with circuitry to read the enemy's mind before he acted. At the heart of this invisible front stood codebreaking. Every army and navy in the world relied on encrypted communication. Orders, coordinates, and plans were transmitted through networks of coded messages. The Axis powers believed their systems unbreakable. Germany used the Enigma machine, an electromechanical device with rotors and plugs that generated billions of cipher variations. Japan used Purple, a complex system of electrical switches that changed patterns daily. To the enemy, these machines promised secrecy. To the Allies, they presented an equation that had to be solved before the war could be won. The task fell to mathematicians, linguists, and engineers, the thinkers of Bletchley Park in Britain and Arlington Hall in the United States. In small wooden huts filled with noise, smoke, and tension, they faced a problem larger than any before it. To break a machine-generated code faster than messages could be sent. Brute force by hand was impossible. The solution was to build a new kind of machine, one that could think through possibilities faster than a human brain. In Britain, this effort produced two breakthroughs. The first was the Bombe, designed by Alan Turing and Gordon Welchman. It tested rotor combinations in the Enigma system by logical elimination. The second was Colossus, the first programmable electronic computer, created by engineer Tommy Flowers to attack the German Lorenz cipher used by High Command. Colossus read paper tapes at 30,000 characters per second and performed logical operations electronically, a leap beyond mechanical calculation. It was the moment when codebreaking became computing. Across the Atlantic, American cryptanalysts tackled the Japanese naval codes, culminating in the decryption of JN-25, which revealed Japanese plans before the Battle of Midway. That intelligence turned the tide of the Pacific War. Later, the Purple Machine's secrets gave Allied strategists deep insight into Japan's diplomacy and military structure. Each decoded message was a silent battle won. Every intercepted signal meant convoys rerouted, ambushes avoided, submarines destroyed. The scale of these operations was enormous. At its peak, Bletchley Park employed more than 10,000 people, mathematicians, typists, engineers, and clerks. Their work was divided into sections that specialized in naval, air, or diplomatic ciphers. Each message passed through rooms of machines, from punch card sorters to paper tape readers, as analysts pieced together meaning from fragments. The process combined human intuition with machine speed, an early form of human-computer collaboration. The secrecy surrounding these efforts was absolute. Even among the participants, few understood the full scope of their mission. Most believed they were engaged in routine analysis. The truth was known only to a handful of commanders and intelligence officers. After the war, many veterans of Bletchley Park never spoke of their work for decades. The entire operation remained classified until the 1970s. The results, however, were decisive. Historians estimate that Allied codebreaking shortened the war by at least 2 years. It neutralized the U-boat threat in the Atlantic, exposed enemy troop movements, and allowed the Allies to anticipate attacks before they occurred. It turned intelligence from a passive resource into an active weapon, predictive, preemptive, and precise. But beyond victory, the codebreakers created something enduring, the architecture of modern computing. The vacuum tubes, relays, and logic circuits of Colossus formed the blueprint for the digital revolution that followed. The mathematical theories developed for cryptanalysis became the foundation of computer science. The same logic that decrypted Enigma would later guide the birth of algorithms, programming languages, and networked communication. In the war's shadow, the first sparks of the information age were lit. The battlefield had shifted from geography to data. The Allies had built machines not just to win a war, but to invent a future. The codebreakers of the 1940s worked for silence, but their machines gave voice to the modern world, a world still shaped by their invisible victory. The story of codebreaking was as much about human patience as technological speed. Every message that reached Bletchley Park or Arlington Hall arrived as noise, a meaningless stream of letters that concealed life and death decisions. The codebreaker's task was to turn that noise into knowledge before the knowledge turned into action on the battlefield. It was a race against time, fought with logic, intuition, and machines that barely existed before the war. At Bletchley, the day began before dawn. Intercept stations scattered across Britain. Y stations captured enemy radio transmissions and relayed them through secure lines. The signals arrived on paper rolls, punched or written by hand, and were sorted into categories: naval, air, army, diplomatic. Linguists grouped similar phrases, analysts searched for patterns, and mathematicians tested theoretical weaknesses in the cipher systems. It was organized chaos, guided by intellect. Each room specialized in a single fragment of the puzzle, none knowing the full picture. Alan Turing's team focused on the German naval Enigma, the most complex version. They used statistical reasoning to identify cribs, or probable words hidden within encrypted text, weather reports, headings, routine phrases. Once a crib was found, it became a thread to pull. The bomb machines, standing in rows and humming with mechanical rhythm, tested hundreds of rotor settings per minute, eliminating impossibilities until a solution emerged. When the correct alignment was discovered, an operator shouted the signal phrase that meant success: "Stop the drums." A day's worth of German naval traffic would then pour open like a flood. The intelligence derived from these decrypts was codenamed Ultra. It was passed to military commands under strict secrecy. Field officers never knew its source, only that it was from a special intelligence. This anonymity protected Bletchley's existence, but also limited how freely commanders could use the information. Nevertheless, Ultra shaped every major campaign after 1941. It exposed the movements of U-boats, revealed Luftwaffe deployment schedules, and predicted enemy logistics. The Battle of the Atlantic was won not just by ships and planes, but by logic tables and typewritten messages from a quiet English estate. In the Pacific, similar efforts unfolded in parallel. American cryptologists, including William Friedman and Agnes Driscoll, worked to break Japanese systems like JN-25 and Purple. They built analog machines called Purple analogs that mirrored Japan's encryption device. These machines, coupled with tireless hand analysis, uncovered Japanese naval intentions before Midway, allowing Admiral Nimitz to position his fleet perfectly for ambush. That victory changed the balance of the Pacific. Codebreaking's progress also demanded new methods of data handling. Each intercept produced thousands of punched cards, sorted by frequency, length, and pattern. This reliance on mechanical data sorting led directly to the design of automatic counting and tabulation machines, precursors to computers. Technicians modified Hollerith tabulators, once used for the census, to manage cryptanalytic data. Mathematics had become machinery. The atmosphere at these centers mixed secrecy with exhaustion. Long shifts under dim light, endless paper streams, and the constant awareness that a missed pattern could cost thousands of lives. Yet morale remained high because every success was immediate and tangible. When decrypted intelligence warned of a submarine attack or exposed a bombing raid, lives were saved the next day. Codebreakers rarely saw battle, but they felt its pulse in every signal they intercepted. As machines like Colossus appeared, the balance shifted from manual labor to electronic speed. Logic circuits replaced fingers and pencils. For the first time, humans built a device not to calculate numbers but to interpret logic, a machine capable of decision within limits. Each victory in decryption pushed computing closer to autonomy. By the war's final year, the partnership between human analysis and machine computation had become seamless. Analysts posed questions. Machines tested answers. Results came faster than any enemy could adapt. The codebreakers had turned the invisible into something measurable, predictable, and conquerable. Theirs was a war of intellect, a war that proved information itself could be a weapon sharper than steel. By the end of the war, the silent intelligence war had become one of the greatest achievements of the modern age. The codebreakers had done more than decrypt enemy messages. They had built the foundation for the computer age. In the dim rooms of Bletchley Park and Arlington Hall, humanity took its first steps toward thinking machines. The logic that cracked ciphers would soon drive transistors, software, and the entire digital revolution. Colossus, completed in 1944, stood at the center of that transformation. It filled a room, glowed with thousands of vacuum tubes, and read paper tape at blinding speed. Its task was to break the Lorenz cipher, used for Hitler's most secret communications. The machine compared streams of code, calculated probabilities, and identified repeating patterns invisible to the human eye. In doing so, it performed logical operations, the very essence of computation. Its creator, Tommy Flowers, had built the first electronic processor, not for science, but for war. Across the ocean, American engineers followed a similar path. The National Cash Register Company, Bell Labs, and Harvard University built electromechanical calculators to aid code-breaking and logistics. The Harvard Mark I, designed by Howard Aiken, could perform automatic sequences of operations, another precursor to the computer. What linked all these machines was purpose, to accelerate thought, to process more information than a human could. The war's need for speed had forced the birth of automation. The end of hostilities revealed how deep that change had gone. The Allies had not simply broken codes, they had invented a new relationship between man and machine. Mathematicians became programmers, their logic converted into circuits. Cryptanalysis became computation. The distinction between intelligence and information vanished. After 1945, many of the scientists who had built wartime machines moved into post-war computing. Alan Turing proposed theoretical models for universal computation. Engineers who had worked on Colossus designed the systems that led to ENIAC and UNIVAC. Intelligence agencies quietly applied electronic analysis to surveillance and data management. The infrastructure of code-breaking became the architecture of modern information systems. But the human element remained central. The codebreakers had learned that even the most advanced machine required intuition. Every cipher revealed not only mathematical structure but human habit, repetition, error, routine. Understanding the enemy's psychology was as vital as understanding his encryption. This union of logic and empathy defined intelligence work in the decades to come. The secrecy around these achievements persisted long after victory. Colossus was dismantled, its existence hidden for 30 years. Official histories barely mentioned Bletchley Park. Only in the 1970s did the truth emerge, that a handful of mathematicians and engineers had quietly altered the course of the war and the course of history. Their success had shortened the conflict, saved millions of lives, and introduced the world to the power of computation. In hindsight, the codebreakers' victory was more than military. It was civilizational. They proved that knowledge could triumph over force, that equations could undo empires, and that silence could shape the future. The machines they built no longer exist, but their logic runs through every circuit, every processor, every screen. In the war's aftermath, the weapons of secrecy became the tools of progress. The first computers, the first algorithms, the first glimpses of artificial intelligence, all were born from the need to read what others wished to hide. The war had forced humanity to create machines that could think faster than men, and in doing so, it had made thought itself the new battlefield. The code breakers of the 1940s never sought glory. They lived and worked in silence, knowing that victory depended on secrecy. Yet their legacy is everywhere, in the rhythm of data, in the hum of servers, in the unseen logic that governs the modern world. They had fought without guns, won without headlines, and built a future their enemies could never imagine. When the Second World War began, infection was often deadlier than the battlefield itself. A soldier who survived a bullet or shrapnel wound could still die from gangrene, pneumonia, or blood poisoning. Medicine had no reliable weapon against bacterial infection. Amputation and hope were the only treatments. Yet within a few years, death from infection would fall by more than 90%. The reason was a quiet revolution born not in an arsenal, but in a laboratory flask, penicillin. Alexander Fleming had discovered the substance in 1928, noticing that a stray mold had killed bacteria on a culture plate. For a decade, the discovery sat dormant, its promise unrealized. In 1940, a team at Oxford University led by Howard Florey and Ernst Chain rediscovered Fleming's work and began testing purified penicillin in animals and humans. The results were astonishing. Infections that had always been fatal simply disappeared. But Britain, under bombardment, could not produce the drug in quantity. The solution came from across the Atlantic. In 1941, Florey's team carried a small vial of penicillin culture to the United States. There, American chemists and engineers turned a scientific curiosity into an industrial process. The U.S. Department of Agriculture's laboratories in Peoria, Illinois, developed deep tank fermentation methods that allowed the penicillium mold to grow by the ton. Pharmaceutical companies, Pfizer, Merck, Squibb, and Eli Lilly, joined forces, trading data instead of guarding patents. It was a wartime collaboration without precedent, competitors becoming allies to save lives. The challenge was biological and mechanical at once. Penicillium was fragile. Its yields were low. Scientists searched the world for better strains, eventually finding a superior one growing on a moldy cantaloupe in an Illinois market. Industrial fermentation tanks, borrowed from the brewing industry, were adapted to provide controlled aeration and temperature. Chemists learned to extract the antibiotic from vast vats of broth and crystallize it into a stable, injectable form. By 1943, American plants were producing enough penicillin to supply every Allied hospital. Its impact at the front was immediate. Before penicillin, 15% of all combat wounds became infected, and septicemia was often fatal. With penicillin, infection mortality in field hospitals dropped below 1%. Soldiers who would once have lost limbs returned to duty within weeks. Surgeons no longer feared deep wounds or abdominal injuries. Pneumonia, meningitis, and syphilis, all major military health problems, became treatable. The drug's quiet power was transforming not only medicine but morale. Wounded soldiers could now believe in survival. The military treated penicillin as a strategic resource. Early supplies were reserved for the armed forces, and doctors were instructed to recycle even urine to recover the precious drug. By D-Day in 1944, every Allied soldier carried the protection of penicillin through the medical corps. It saved tens of thousands of lives in Normandy alone, and countless more across Europe and the Pacific. The Axis powers, isolated from the discovery, tried to synthesize substitutes, but never succeeded in mass production. Behind the miracle lay a deeper transformation. Penicillin proved that biology could be engineered, that microbes could be harnessed as factories. It created the field of industrial microbiology and opened the path for later antibiotics, vitamins, and vaccines. The collaboration between universities, government, and private companies during the penicillin program became the template for modern biomedical research. When the war ended, penicillin's production lines did not shut down. They expanded. Civilian hospitals around the world gained access, and the once fatal infections of everyday life receded. Childbirth, surgery, and ordinary wounds became safe. The drug's discoverers received the Nobel Prize in 1945, but its true reward was measured in lives preserved. Penicillin did not win battles or destroy enemy armies, yet its effect on victory was undeniable. It kept soldiers fighting, reduced logistical burdens, and symbolized the humane side of technological warfare. It reminded a world consumed by machines that salvation could come from something as small and silent as a spore. It was the most compassionate weapon ever made, a cure forged in war, and humanity's proof that science could heal faster than war could kill. Mass production of penicillin became one of the greatest engineering feats of the war. What began as an academic experiment in a handful of glass flasks turned into an industrial network stretching across the United States. The task required solving problems that had never existed before: how to grow tons of delicate mold, how to extract its product without destroying it, and how to maintain purity on a factory scale. Chemists, engineers, and microbiologists collaborated under immense pressure, building a new kind of industry in less than 2 years. The solution lay in deep tank fermentation, a process adapted from beer brewing. Engineers redesigned fermentation tanks with precise temperature, aeration, and nutrient control, creating ideal conditions for the penicillium mold to thrive. Yet even with perfect conditions, yields were low. The mold itself was unpredictable, sometimes weak, sometimes potent. The breakthrough came when researchers found a naturally high-producing strain on a rotting cantaloupe in a Peoria market. With this strain, production increased 100-fold. Extraction was another battlefield. Penicillin was unstable and degraded quickly in heat or acid. Chemists learned to isolate it using cold filtration and solvent extraction. At first, only a few milligrams could be recovered per liter of broth. By 1943, the yield had multiplied 1,000 times. Each discovery, better corn-steep liquor for nutrients, optimized oxygen flow, new crystallization techniques, pushed production closer to military demand. By 1944, American plants were producing more than 100 billion units of penicillin each month. The collaboration among private companies defied normal business logic. Pfizer, Merck, and Squibb shared research openly under government coordination. Patents were ignored. Secrecy gave way to urgency. Factory engineers worked side by side with academic biologists, translating laboratory protocols into continuous industrial operations. For the first time, biology was treated like engineering, quantified, standardized, scaled. The process became a model for every biotechnology program that followed. On the battlefield, the effects were visible in the statistics of survival. Before penicillin, 18% of soldiers wounded in action died from infection. With penicillin, that number fell below 1%. Field hospitals transformed from places of slow decay into centers of recovery. Penicillin-treated wounds closed cleanly. Operations once considered suicidal became routine. Amputations dropped sharply. The psychological effect was immense. Soldiers no longer feared the slow death of infection. Penicillin's influence extended beyond treatment. It transformed logistics and planning. Armies no longer needed to evacuate wounded men immediately. Mobile surgical units could operate close to the front, stabilizing casualties who once would have perished before reaching a hospital. Fewer deaths meant less strain on manpower and morale. The drug became as essential to Allied success as fuel or ammunition. The Allies guarded their advantage carefully. While German scientists understood the principles of antibiotics, the lack of resources and industrial infrastructure prevented them from achieving mass production. Japan's efforts were even more limited. By the time the Axis realized the scale of Allied output, it was too late. The miracle mold had already become a strategic weapon. By war's end, penicillin symbolized a new relationship between science and warfare. It proved that technology could heal as well as destroy, that the same industrial systems producing bombs could also produce cures. The campaign to manufacture penicillin changed not only medicine, but the very idea of what science could do under pressure. It showed that cooperation, not competition, could achieve the impossible. When the final battles ended and soldiers returned home, the factories did not close. They shifted to civilian production, flooding the world with medicine instead of munitions. In a war built on destruction, penicillin stood as its quiet opposite, proof that even in humanity's darkest moment, science could choose to save. By the final year of the war, penicillin had become not just a drug, but a symbol of civilization fighting back against chaos. It represented the idea that knowledge itself could be a weapon more powerful than any bomb. On every front, from the beaches of Normandy to the jungles of the Pacific, medics carried vials of the golden liquid that turned death into recovery. The number of lives it saved is impossible to count, but its influence reached far beyond the battlefield. In hospitals from London to Manila, wounded soldiers once written off as hopeless were standing again within days. Pneumonia cases that had killed pilots and submariners alike were now curable. Infections from burns, shrapnel, and surgery no longer spread uncontrollably through field wards. Even sexually transmitted diseases, a chronic military problem, were now treatable, restoring both health and morale. The change was so complete that it altered military medicine itself. Surgeons began operating more boldly, knowing infection would no longer finish what enemy weapons had started. Penicillin's victory reshaped the relationship between medicine and state power. The same centralized planning, mass production, and scientific cooperation that had built radar and proximity fuses now built a cure. The U.S. War Production Board coordinated every step, from corn processing to refrigeration. Pharmaceutical firms learned logistics from the military. The military learned medicine from scientists. It was a synthesis of war and healing, a reminder that industrial might could also serve life. After the war, the momentum did not stop. The facilities that had produced penicillin for the Army were redirected to serve civilians. Hospitals worldwide gained access, and within a few years, diseases that had defined human suffering for centuries, pneumonia, meningitis, septic wounds, became treatable. Other antibiotics soon followed: streptomycin, chloramphenicol, tetracycline. Each traced its lineage to the same wartime laboratories and fermenters that had birthed penicillin. A medical revolution had begun, its origins not in peace but in total war. For the soldiers who lived because of it, penicillin meant more than survival. It meant proof that progress could still exist amid destruction. Letters home often spoke not of weapons or battles, but of gratitude toward a drug they barely understood. Generals credited it as a force multiplier equal to a new division. Statistically, it returned tens of thousands of men to combat and saved hundreds of thousands more from death. No other medical innovation had ever changed warfare so profoundly, not by killing more efficiently, but by keeping men alive. In the greater history of technology, penicillin stands beside radar and the atomic bomb as one of the three decisive scientific breakthroughs of the Second World War. Yet it alone worked entirely in the service of life. Its success marked the beginning of modern pharmacology, industrial microbiology, and global health policy. It proved that the tools of war could be turned toward healing, and that the most effective form of victory was survival itself. When peace finally came, penicillin was already shaping a different world. Civilians received it by prescription, children recovered from infections once fatal, and entire hospitals reorganized around antibiotic treatment. The mold that had once grown unnoticed in a London lab now stood as a monument to human ingenuity. In the age of total war, it was the quiet revolution, the invisible salvation that fought not against an enemy, but against death itself. In the early months of World War II, air defense still rested on old-fashioned eyes and searchlights. Aircraft emerged from darkness, dropped their ordnance, and slipped back into night. Tracking them relied on sound or visual spotting. By 1939, radio engineers had begun solving a different problem: how to see what the eye could not. Radio waves could bounce off metal and water like light, but they penetrated haze, darkness, and weather. That offered a way to detect aircraft and ships beyond human vision. The U.S. Navy's first operational sets entered limited service around 1940. At its core, radar sent a pulse of radio energy, waited for the echo, and calculated distance and bearing. Suddenly, a ship could detect an enemy plane before the pilot saw the ship's guns. Engineers then pushed radar from long wavelengths to centimetric wavelengths. The development of compact, high-power magnetrons allowed radars to operate at much shorter wavelengths, shrinking antenna size and raising resolution. Aircraft and ships could now carry practical microwave sets. Radar changed doctrine as much as capability. Early warning stations relayed target tracks to controllers who vectored interceptors and directed anti-aircraft fire. A single radar set could serve multiple guns and aircraft, extending vision through darkness and bad weather and turning passive defense into proactive engagement. Surface search radars allowed convoys to spot submarine periscopes and surface threats at ranges that made surprise attacks far more difficult. Production and training were decisive. By 1943, thousands of radar units were installed on ships, aircraft, and shore stations. Industrial lines turned out antenna arrays, magnetrons, vacuum tube electronics, and display equipment at scale. Each installation required trained operators, maintenance crews, and secure communications links. The collective effect was multiplier. Radar units coordinated into networks multiplied the effectiveness of fighters. anti-aircraft batteries, and escort vessels. Operational impact was immediate and measurable. In the Atlantic, radar-equipped escort ships and long-range aircraft severely reduced U-boat effectiveness by detecting periscopes and night surface attacks. In the Pacific, radar allowed task forces to detect incoming air raids before visual contact, improving reaction times and defensive firing solutions. Night engagements, previously the domain of luck and local skill, became matters of coordinated detection and guided response. Radar also reshaped offensive operations. Bombers used radar for navigation and target identification through cloud and darkness, maintaining strategic pressure where visual bombing had been limited. Naval gunfire support benefited from fire control radars that measured range and corrected trajectories. The same principles that made radar valuable in defense enhanced accuracy and coordination in attack. Limitations existed. Early radar suffered from range ambiguities, ground or sea clutter, and operator error. Systems required power, cooling, and continuous maintenance. Enemy countermeasures, jamming, deception, and tactics exploiting radar blind spots forced continual adaptation. Yet American industry and research sustained that adaptation with rapid improvements in electronics, signal processing, and antenna design. Beyond wartime effects, radar's legacy extended into post-war aviation, meteorology, and guided weapons. The wartime push for rugged, mass-producible microwave electronics accelerated developments that later enabled air traffic control, weather observation, and missile guidance. Methodologically, radar projects reinforced the model of concentrated civilian-military collaboration and rapid production scaling. In strategic terms, radar converted information into force. It allowed commanders to act on knowledge rather than guesswork, to allocate scarce resources where threats were detected, and to deny the enemy the advantage of surprise. In a conflict defined increasingly by speed and range, radar supplied the indispensable faculty of sight, and with sight came control. As the war progressed, radar evolved from an experimental tool into a vast, integrated system. Each new model was smaller, more reliable, and more specialized. Aircraft-mounted radars detected enemy formations long before visual range. Ships coordinated radar contacts with gunfire control computers, converting echoes on screens into precise firing solutions. For the first time, naval engagements could be fought in total darkness. In the Solomon Islands and later at Leyte Gulf, American task forces used radar to locate and destroy Japanese vessels hours before sunrise, striking enemies who never saw them coming. Radar became a weapon of command and timing. In the Pacific, early warning stations across island chains fed information to fighter-director ships. These command centers plotted approaching aircraft and vectored interceptors to intercept waves of attackers miles from the fleet. The system transformed chaotic air battles into coordinated defenses. Each blip on the radar scope represented lives saved, ships protected, and attacks defeated before they began. In Europe, radar defined the air war over Britain and later Germany. The British chain of coastal radar stations provided the first operational model of an integrated air defense network, and the United States built upon that idea. American stations protected key industrial centers and coordinated with night fighter units equipped with airborne radar. The result was unprecedented situational awareness. Pilots who once relied on eyesight and luck could now hunt bombers through cloud and darkness, guided only by the glow of an oscilloscope. Technology continued advancing at breakneck speed. New microwave radars use shorter wavelengths, providing sharper resolution and allowing for compact antenna arrays on fighter aircraft. Bombing accuracy improved as radar navigation sets allowed bombers to locate cities and industrial targets even through thick overcast. Radar altimeters enabled precise low-level flight, vital for torpedo bombers and ground attack missions. These instruments transformed aviation into an all-weather, round-the-clock operation. At sea, radar's influence was even more visible. Escort carriers, destroyers, and submarines all carried radar for detection and coordination. In the Atlantic, radar-equipped patrol planes shattered the effectiveness of the German U-boat fleet. Submarines that once surfaced at night to recharge batteries were now spotted instantly, even in fog or moonless conditions. The technological edge shifted decisively to the Allies. U-boat losses mounted, and by 1944, Admiral Dönitz admitted that Allied radar had rendered his wolf packs blind and vulnerable. On land, radar served new roles. Artillery units used ground-based radar to track shells in flight, correcting fire in real time. Weather radars began providing forecasts for air operations. Field commanders could now plan bombardments and sorties with unprecedented precision. Every part of modern warfare, air, sea, and ground, had begun to depend on invisible waves of radio energy. Radar's impact was not merely tactical. It was psychological. The enemy could no longer strike unseen. Surprise, once a weapon of the attacker, now belonged to the defender. It changed the rhythm of combat itself, forcing adversaries to fight under constant observation. In a war where speed and deception had once reigned, radar reintroduced certainty, discipline, and control. It gave the Allies not just eyes in the dark, but confidence in the unknown. By 1945, radar had become the silent commander of modern warfare. Its presence extended from the smallest patrol plane to the largest fleet carrier, from Arctic convoys to jungle airstrips in the Pacific. What began as a handful of experimental transmitters had turned into an electronic nervous system connecting every branch of the armed forces. Each radar pulse carried more than data. It carried control, anticipation, and dominance. In naval battles, radar dictated the rhythm of engagement. At Leyte Gulf and Surigao Strait, American battleships and cruisers used radar-directed fire to annihilate Japanese formations long before visual contact. Destroyers maneuvered in darkness using radar bearings, coordinating torpedo attacks with mathematical precision. The sea, once ruled by visibility and chance, had become an instrument of geometry and reflection. Commanders no longer relied on instinct. They relied on echoes. Every decision, when to turn, when to fire, when to retreat, depended on the clarity of a radar screen. In the air, radar turned chaos into order. Ground-controlled interception systems guided waves of fighters into precise interception paths. Airborne radar allowed night fighters like the P-61 Black Widow to hunt bombers invisibly. Strategic bombers, once limited by weather, now struck their targets through cloud and darkness using radar bombing systems. The glow of cathode ray screens replaced the horizon. The hum of transmitters replaced the eye. The skies, once the enemy's escape, became a transparent battlefield. Technologically, radar forced a revolution in electronics. The wartime push for compact, rugged components drove innovations in vacuum tubes, waveguides, and power supplies. The magnetron, the heart of microwave radar, became one of the most influential inventions of the century, forming the basis of post-war radar, communications, and even microwave ovens. Engineers learned to stabilize frequencies, filter signals, and process echoes, giving rise to the first concepts of real-time electronic computation. The collaboration between the MIT Radiation Laboratory, Bell Laboratories, and the US military forged the industrial scientific model that would dominate the Cold War. Strategically, radar redefined intelligence. The ability to detect, track, and coordinate at long distances shifted warfare from reaction to prediction. Commanders no longer guessed, they calculated. Convoys altered course before submarines arrived. Air raids were intercepted hours before impact. Even deception became more complex, as both sides began to explore radar jamming, decoys, and stealth tactics. The electromagnetic spectrum itself had become a battlefield, one that would remain contested long after 1945. When the war ended, radar was no longer a secret. It was a foundation. Civilian air traffic control, meteorology, and navigation all descended from wartime systems. Radar's disciplined precision replaced improvisation as the hallmark of modern warfare. It gave the Allies not only superiority but foresight, transforming defense into preemption and uncertainty into information. The invisible waves that once guided shells and aircraft now defined the modern world. From guided missiles to space tracking, from weather forecasting to global navigation, radar's pulse still echoes in every technology that measures, detects, and decides. It was the first instrument that allowed humanity to see beyond sight, to perceive through darkness, clouds, and distance. In World War II, radar was not a weapon in the traditional sense. It did not kill or destroy, but it made every weapon smarter, every commander faster, and every defense stronger. It was the quiet intelligence behind victory, the signal that turned the tide before a single shot was fired. In June 1944, as Allied soldiers stormed the beaches of Normandy, one machine made the impossible possible, a flat-bottomed wooden vessel with a steel ramp at its bow. It was not fast, armored, or elegant, but it carried armies through surf and gunfire onto the enemy's shore. Its official name was LCVP, Landing Craft, Vehicle, Personnel, but history remembers it as the Higgins boat, after its inventor Andrew Jackson Higgins. It was the boat that opened a continent. Before its arrival, amphibious warfare was a logistical nightmare. The U.S. Navy lacked a vessel that could land men and vehicles directly onto a hostile beach. Traditional landing craft forced troops to jump overboard into deep water, often drowning under heavy packs or enemy fire. Higgins, a boat builder from New Orleans who specialized in shallow draft swampcraft, had already solved a similar problem for Louisiana's marshes: how to move heavy loads through water only a few feet deep. His design used a flat bottom, a protected propeller, and a steel ramp that dropped to unload cargo directly onto shore. When the Marines tested it in 1941, they realized it was the missing piece of modern invasion warfare. The ramp allowed men, jeeps, and supplies to exit in seconds. Higgins modified his swamp boat into a military workhorse, 36 feet long, powered by a diesel engine, carrying 36 soldiers or a 3-ton vehicle. It could operate in just 18 inches of water and back away from the beach without grounding. Its hull was made of simple plywood and steel fittings, cheap, fast to build, and easy to repair. By the time America entered the war, Higgins Industries had turned its small New Orleans workshop into a vast production empire. Using a network of subcontractors and assembly lines, Higgins employed over 20,000 workers, welders, carpenters, and engineers, including many women and black laborers, at a time when segregation was still law in much of the country. His shipyards became one of the first fully integrated workplaces in America. Efficiency was his weapon. He built boats faster than the military could request them. The Higgins boat soon became the backbone of every Allied amphibious operation. In the Pacific, it carried Marines ashore at Guadalcanal, Tarawa, and Iwo Jima. In North Africa and Sicily, it delivered troops under fire against fortified beaches. And on D-Day, more than 1,000 Higgins boats led the assault on Normandy. Each wave of gray ramps opening on the sand became the living symbol of invasion itself. The boat's design proved so simple and effective that it required almost no modification throughout the war. Soldiers called it the wooden wonder. Commanders called it indispensable. It allowed generals to plan operations that had once been unthinkable, not just to attack ports, but to create ports anywhere by force. The Higgins boat turned geography itself into a weapon. Dwight D. Eisenhower later said that without Andrew Higgins, we never could have landed over an open beach. The whole strategy of the war would have been different. What he meant was that Higgins didn't just build boats. He built mobility. He turned coastlines from barriers into gateways, giving the Allies the power to strike anywhere, at any time. When the war ended, nearly 23,000 Higgins boats had been built. They carried not only men and vehicles, but the very concept of industrial improvisation, a simple, functional design mass-produced into strategic advantage. The Higgins boat was never meant to be heroic. It was a box with an engine and a ramp. But in its simplicity lay genius. It was the bridge between sea and land, between industry and victory. Every landing, every liberated city, every step taken toward Berlin and Tokyo began with its steel ramp hitting sand. The story of the Higgins boat was as much about invention as it was about transformation, of technology, labor, and the very concept of amphibious war. Andrew Jackson Higgins was not a naval officer or a government engineer. He was a civilian entrepreneur from Louisiana who built workboats for oilmen and loggers. His shallow draft boats were designed for speed through bayous and swamps, not battlefields. Yet his stubborn belief in practicality over bureaucracy forced the U.S. military to rethink its entire approach to landing operations. When the Navy first tested his designs in the late 1930s, officials dismissed them as too unconventional. Naval doctrine favored large landing barges and heavy steel craft, not plywood boats. Higgins fought back, arranging his own demonstrations. He invited officers to New Orleans, drove his boat straight up onto the Mississippi mudbanks, unloaded cargo, and backed out again. The skeptics had no counter-argument. His boat worked. The Marines saw its potential first, and by 1940 they had convinced Washington to fund prototypes. Within a year, the LCVP had become standard issue. Higgins's genius lay not only in the design, but in his method of production. He approached boat building like automobile manufacturing, modular, fast, and decentralized. He recruited from everywhere: carpenters, dock workers, mechanics, and housewives. In his yards, women assembled hull frames and engines, while black craftsmen and engineers held supervisory roles rare for the time. "The only color that counts here," Higgins famously said, "is the color of production." His yards became a social revolution wrapped in steel and wood. The boats themselves reflected the same philosophy: simplicity, efficiency, reliability. Each one used standardized components and minimal materials. Plywood for the hull, mild steel for the ramp, and a single diesel engine meant rapid repair and low cost. They were designed to be expendable. If a boat made it through a few landings, it had already earned its worth. Crews learned to maintain them with basic tools, sometimes patching bullet holes with tin and nails between assaults. Combat proved their worth beyond any expectation. In the Pacific, Higgins boats became the spearhead of island hopping, carrying troops onto beaches where no port existed. They faced coral reefs, surf, and machine gun fire, yet kept coming. The ability to unload vehicles directly onto land allowed engineers to build airstrips and supply bases within hours. Each landing tightened the noose around Japan's empire. In the Mediterranean, the same craft delivered troops during Operation Torch. Sicily and Salerno, testing the concept that would culminate in Normandy. At Omaha Beach, under the storm of artillery and gunfire, Higgins boats kept moving. Waves of them approached through the surf, their ramps slamming down into chaos as soldiers leapt into the water and sand. Many were destroyed within minutes, but more came behind them, line after line, hour after hour. By the end of D-Day, nearly every soldier who stepped onto the French coast had done so from a Higgins boat. The invasion that freed Europe had ridden on Louisiana wood. Behind those landings was an industrial miracle. Higgins's factories produced more than 20,000 landing craft of various models, LCVPs, LCMs, and PT boats, at a pace no traditional shipyard could match. Every 30 minutes, another boat rolled out of his assembly lines. His success was so complete that the Navy admitted its own shipyards could not compete with his methods. Eisenhower, Churchill, and Roosevelt all credited him personally for giving the Allies the means to cross oceans and break fortresses. The war had many generals, but only one boat builder changed its geography. By 1945, the Higgins boat had become more than a machine, it was a doctrine. Every major Allied invasion, from North Africa to the Philippines, depended on its design. Its flat hull, retractable ramp, and shallow draft allowed entire armies to bypass ports, strike at will, and establish beachheads where the enemy least expected. The war that had once been bound by geography was now mobile, amphibious, and unpredictable, and that transformation began in a New Orleans workshop. The scale of production was staggering. Over 23,000 Higgins boats were built during the war, each one stamped with the same simple purpose: carry men and vehicles from ship to shore, no matter the cost. They came off assembly lines faster than any other craft of the war, built not by naval shipwrights but by ordinary Americans, women, black laborers, and unskilled workers trained on the job. The Higgins Industries workforce reflected the democratic ideal it was fighting for: inclusion, equality, and unity in pursuit of a single goal: output. The boats themselves became icons of industrial minimalism. They were not elegant or comfortable, but every detail served function. The ramp was designed to drop in under 2 seconds. The hull could scrape through surf and coral without splitting. Even if damaged, the craft could limp back to its transport for repairs. They could carry 36 men, a jeep, or small artillery pieces. When massed together in formation, they turned an ocean into a road, an assembly line delivering freedom, one wave at a time. Their psychological impact was immense. Soldiers remembered the deafening engines, the salt spray, the ramp slamming open, and the sudden chaos of beach landings. To many, that moment, the drop of the ramp, defined their entire war. It was the point where planning met reality, where steel and human will collided with fire. The Higgins boat was both vehicle and threshold, the last place of safety before war, and the first step into history. Even after the war, the Higgins design continued to shape military thinking. Its descendants became the blueprint for every modern landing craft, from Korea to Vietnam, from the Falklands to the Persian Gulf. The concept of modular amphibious transport, conceived in Louisiana's swamps, became a permanent pillar of military logistics. The idea that an army could create its own port, anywhere on Earth, redefined strategic mobility for generations. Andrew Higgins himself returned to civilian life without fanfare. He built pleasure boats, experimented with high-speed designs, and continued to advocate for racial integration in industry. But his wartime legacy endured. Eisenhower's words, "He is the man who won the war for us," were not exaggeration. Without Higgins's boat, there could have been no Normandy, no island landings, no Allied advance across two oceans. Today, a few surviving Higgins boats rest in museums, their wooden hulls weathered but intact. Visitors walk their decks and see simplicity: planks, bolts, an engine, a ramp. Yet in that simplicity lies one of the greatest military innovations of the 20th century. The Higgins boat turned oceans into pathways and beaches into gateways. It was the vessel that carried the free world to victory, built not for glory, but for purpose. A boat that did not conquer by power, but by access. The craft that opened a continent, one landing at a time. In the summer of 1939, a single letter changed the course of history. It was written by Albert Einstein and physicist Leo Szilard, warning President Roosevelt that recent discoveries in nuclear fission might allow Germany to build a new kind of bomb, one capable of destroying an entire city in a single blast. Within 3 years, that warning became the Manhattan Project, the largest scientific and industrial effort in human history. It would unite thousands of scientists, engineers, and soldiers in a race to harness the energy locked inside the atom, and it would end the war by redefining power itself. At its core, the Manhattan Project was an experiment in scale. It began as a theoretical question. Could uranium be split fast enough to sustain an explosive chain reaction? But theory quickly demanded industry. The U.S. Army Corps of Engineers under General Leslie Groves built secret cities to house laboratories and reactors. Oak Ridge in Tennessee enriched uranium, Hanford in Washington produced plutonium, and Los Alamos in New Mexico became the design center for the bomb itself. Entire towns were fenced, guarded, and erased from maps. More than 100,000 people worked behind locked gates, each knowing only a fragment of the whole. The scientific challenge was immense. Uranium existed in 2 isotopes, but only uranium-235 could sustain a chain reaction, and it made up less than 1% of natural ore. Separating it required massive electromagnetic and gaseous diffusion plants. At Hanford, reactors bred plutonium from uranium-238, creating an entirely new element, a metal that had never existed on Earth in significant quantity before the war. Each breakthrough demanded new physics, new engineering, and new courage. Every mistake risked contamination, explosion, or death. At Los Alamos, physicist J. Robert Oppenheimer assembled the greatest concentration of scientific talent ever gathered. Men like Fermi, Feynman, Teller, and Bohr. Their task was to turn invisible theory into a working weapon. 2 designs emerged: a uranium bomb using simple gun-type assembly and a plutonium bomb requiring implosion by synchronized explosive lenses. Precision was absolute. The timing of detonators had to be perfect to within microseconds. The calculations were done by hand, by slide rule, by teams of women known as computers. Their work was the arithmetic of apocalypse. While the scientists labored in desert isolation, the factories behind them consumed resources on a continental scale. Oak Ridge alone used more electricity than New York City. Trains carried uranium ore from Africa and Canada under armed guard. Chemical companies built special materials to withstand the heat and radiation of new reactions. Every element of modern logistics, rail, power, chemistry, and computation, was absorbed into the single goal of release, the splitting of the atom. Secrecy was total. Few in government knew what was being built. To most workers it was the gadget. Security clearances divided even the elite. Physicists were forbidden from discussing designs across groups. The isolation created an atmosphere of intense focus and growing moral unease. As the weapon took shape, its builders began to understand that they were creating something beyond all precedent, a force that could destroy civilization as easily as it could end the war. On July 16, 1945, the desert of New Mexico turned to light. The first atomic explosion, codenamed Trinity, vaporized the sand into glass and sent a shockwave felt 100 miles away. Oppenheimer watched through darkened goggles and recalled a line from the Bhagavad Gita. "Now I am become death, the destroyer of worlds." The equation had worked. Humanity had split the atom, and with it, its own innocence. 3 weeks later, 2 bombs ended the war. Little Boy fell on Hiroshima on August 6th, Fat Man on Nagasaki 3 days later. Over 100,000 people died instantly, and many more in the weeks that followed. Japan surrendered. The Manhattan Project had achieved its purpose, but at a cost no one could measure. The weapon had ended one war and begun a new one, the Cold War, an age of perpetual atomic tension. The project's legacy reached far beyond the battlefield. It transformed science into a branch of state power. The fusion of government funding, military organization, and scientific research became the model for all later technological programs, from nuclear energy to space exploration. It also redefined the ethics of discovery. The same minds that had unlocked the atom now struggled with the question of whether knowledge itself could be too powerful to control. In the years after the war, the laboratories at Los Alamos and Hanford became the foundations of the nuclear age. Reactors that once bred plutonium now generated electricity. The same chain reactions that destroyed cities now lit them. Yet the shadow of the Manhattan Project never faded. It proved that science could command forces once reserved for gods, and that once created, those forces could never be undone. The Manhattan Project was the ultimate expression of the 20th century's faith in progress, and its greatest warning. It showed that reason could conquer nature, but not necessarily control the consequences. It was both triumph and tragedy, the moment humanity realized it could end war, or end itself. The Manhattan Project's power lay not only in its physics, but in its organization. It was the first time science, industry, and the military operated as one. General Leslie Groves managed the project with the precision of an army campaign, while Oppenheimer led its intellectual front. Together they created a new model for warfare, one where equations and logistics mattered as much as tactics and courage. The system Groves built was staggering in scope. Oak Ridge, Hanford, and Los Alamos were not laboratories but entire cities, built from nothing in months. Oak Ridge spread across 60,000 acres of Tennessee hills, its miles of power lines feeding the vast electromagnetic separators known as calutrons. These machines isolated uranium-235 atom by atom, consuming enormous energy. Hanford, hidden along the Columbia River, operated nuclear reactors that bred plutonium inside uranium fuel rods. Workers handled materials they barely understood under layers of secrecy and radiation shielding. At Los Alamos, the intellectual heart of the project, physicists converted that material into weapons of precise geometry and unimaginable force. The logistics of secrecy rivaled the engineering. Mail was censored. Telephones were monitored. Scientists were forbidden from leaving without permission. Even their families lived under coded addresses. Most of the 125,000 workers never knew what they were making. They refined uranium, welded casings, assembled circuits, each task a fragment of a puzzle known only to a handful of men in a desert laboratory. Inside that laboratory, the science moved at the edge of possibility. To trigger a chain reaction, fissile material had to reach a critical mass in microseconds. The uranium bomb, Little Boy, used a simple gun-type mechanism that fired one subcritical mass into another. But plutonium, created at Hanford, behaved differently. It emitted spontaneous neutrons that could cause premature detonation. The solution was implosion, compressing a plutonium core inward, with synchronized explosive charges to reach supercritical density. The challenge was synchronization. Detonators had to fire within millionths of a second of each other. This required new mathematics, new materials, and new precision tools. Metallurgists learned to shape plutonium without cracking it. Explosives experts built lenses of varying density to bend shockwaves uniformly. Engineers invented fast electronic circuits capable of timing with unheard-of accuracy. The entire process was a lesson in controlled chaos, theory converted into machinery at the edge of what humans could measure or imagine. Oppenheimer's leadership gave the chaos order. He fused physicists, chemists, and military officers into a single working unit. Arguments were frequent, failures constant, but progress never stopped. At night, scientists debated quantum mechanics in the dining halls. By day, they tested explosives in the desert canyons, measuring flashes with high-speed cameras. Every breakthrough led to a new crisis, and every crisis drove invention. The bomb was not built in a straight line. It was wrestled into existence by intellect and urgency. Parallel to the science, moral unease grew. Many of the physicists were refugees from Europe who had fled the Nazi regime. They feared that Germany was racing toward the same goal. But by 1944, when evidence showed that Germany's nuclear program had failed, their motivation shifted. They were no longer preventing a German bomb. They were creating an American one. Some urged restraint. Others believed that only demonstration through use could justify the cost. No one yet understood how absolute the weapon's power would be. By mid-1945, the project had consumed $2 billion, more than any single engineering effort in history. It had mined continents, built factories the size of cities, and generated technologies that would define the next century. Yet it all narrowed to one point: a small metal sphere, no larger than a basketball, waiting in the desert to prove whether humanity could command the atom or be consumed by it. The scientists called it simply the gadget. Its detonation at Trinity would test not only their equations, but their faith in knowledge itself. The success of that single blast would signal that mankind had crossed a threshold, from discovering nature's laws to rewriting them. At dawn on July 16, 1945, the desert at Alamogordo, New Mexico, became the proving ground of human intellect and consequence. The bomb stood on a steel tower, its core of plutonium surrounded by lenses of high explosive wired with perfect symmetry. At 5:29 a.m., the countdown reached 0. A light brighter than the sun tore through the sky, followed by a wave of heat that turned sand to glass and shook the mountains. The first atomic explosion, Trinity, had worked. The equations were real. In the control bunker, silence fell. For seconds no one spoke. Oppenheimer's mind reached back to the Bhagavad Gita. Now I am become death, the destroyer of worlds. Others cheered, some wept, some stood still, unable to grasp what they had seen. The blast yielded about 20 kilotons of TNT, a number that meant little compared to the reality it represented. The desert glowed with its own sunrise. Humanity had entered the atomic age. Within weeks, the weapons built from that experiment were prepared for use. On August 6th, Little Boy, the uranium bomb, was dropped on Hiroshima. 3 days later, Fat Man, the plutonium bomb, fell on Nagasaki. Both cities were erased within moments. The heat incinerated buildings, vaporized human beings, and left radiation lingering in the air. Over 100,000 lives vanished in seconds. Japan surrendered soon after. The war that had consumed the world ended, not with armies meeting in battle, but with a single detonation. The Manhattan Project had achieved its purpose, but its success carried a burden. The same science that had liberated the world from fascism had also shown how easily civilization could destroy itself. Many of the project's scientists were shaken. Some resigned, others turned to advocacy, warning of a future where war would mean annihilation. The weapon they had built was no longer a secret. It was a precedent. In its shadow, a new kind of war began. One fought not for territory, but for survival. The legacy of the Manhattan Project extended far beyond Hiroshima and Nagasaki. It had fused government, science, and industry into a single mechanism of creation and control. Its laboratories became the seed of the Cold War's atomic complex. Los Alamos, Hanford, and Oak Ridge continued producing nuclear materials for bombs, but also reactors for power and research. The project's organization became the model for future national programs: the hydrogen bomb, the space race, and the development of computing. Technologically, the project pushed the boundaries of every field it touched. Reactor design, metallurgy, chemistry, electronics, all advanced decades in just a few years. The need for fast calculations spurred early work on digital computers. The precision machining of nuclear cores led to new standards in measurement. Nuclear physics itself became an instrument of policy. Knowledge had become a strategic resource. But beyond the science, the moral dimension of the Manhattan Project defined the rest of the century. It forced humanity to confront a question it had never faced before, not whether it could build something, but whether it should. Power and destruction had become identical. Every invention that followed would carry the same question in its shadow. Oppenheimer, once the architect of the bomb, became its conscience. He warned that the weapon's success had turned science into sin. In 1954, he was stripped of his security clearance, a symbol of the new tension between knowledge and authority. Yet his creation remained. The world's balance of power now rested on fission, a fragile peace enforced by fear. In the end, the Manhattan Project was not only the end of one war, but the beginning of a new era. It proved that the mind could master nature at its deepest level, and that mastery was irreversible. From the light of Trinity to the fire over Hiroshima, it marked the moment humanity stepped across a threshold it could never recross. The bomb was not just a weapon, it was a mirror. In its reflection, humanity saw both its genius and its peril, and learned that the cost of ultimate knowledge is never fully known until after it is paid. In the early 1940s, air power was rewriting the rules of war. Aircraft flew faster and higher, carrying heavier payloads and striking from beyond the reach of traditional defenses. Anti-aircraft artillery, once decisive, was falling behind. Gunners relied on timed or contact fuses that demanded precise calculations or direct hits, nearly impossible against fast-moving targets. Thousands of shells were fired for every aircraft destroyed. The problem was clear. Existing weapons could no longer keep pace with modern flight. America's engineers began searching for a technological solution, something that could make artillery intelligent. The answer would come not from a new gun, but from a new kind of fuse. Instead of exploding on impact or after a preset delay, this device would sense when it was near its target and detonate automatically. The idea was rooted in radar principles. A small radio transmitter inside the shell would send out a signal, and when that signal bounced back from an approaching object, it would trigger the explosion. In theory, the concept was elegant. In practice, it bordered on impossible. Miniaturizing radar into a projectile barely a few inches wide, capable of surviving the shock of launch, was unlike anything engineers had attempted. The United States began developing the proximity fuse in 1940, coordinating efforts through the newly established Office of Scientific Research and Development. The Navy wanted protection for its fleets against dive bombers and torpedo planes. The Army needed artillery that could stop massed infantry attacks and low-flying aircraft. Scientists at Johns Hopkins University's Applied Physics Laboratory took charge of the design, working with industrial partners such as RCA, General Electric, and Western Electric. Their mission: create an electronic brain that could survive a cannon's violence and think for a fraction of a second in flight. Every obstacle seemed absolute. A fired shell experienced more than 20,000 times the force of gravity. Its body spun thousands of revolutions per minute, and temperatures soared as it left the barrel. Conventional vacuum tubes shattered instantly under those stresses. Batteries failed from the shock. Circuits shorted before they could even activate. Yet the engineers refused to scale back the goal. They redesigned the tubes with metal ceramic casings, invented flexible filaments that could bend without breaking, and developed tiny reserve batteries that activated only after the projectile was airborne. Each improvement was a battle of materials and precision manufacturing. Testing began in 1942. Most trials ended in failure, premature detonations, duds and misfires. But the cycle of testing and redesign was relentless. Components were tested under simulated launch stresses, circuits refined, and new configurations tried. The engineers learned that perfection was impossible. Reliability was the goal. If most shells worked, the tactical effect would still be revolutionary. Slowly, through hundreds of small improvements, the proximity fuse began to function consistently. By mid-1943, the Navy approved limited deployment. The Pacific Theater would be its first test. Japanese air attacks on U.S. fleets were relentless, and conventional flak guns could rarely score hits before bombers dived. The new fuses changed that. Now, shells exploded close to their targets, spraying lethal fragments through aircraft formations. Pilots reported that American fire suddenly seemed alive, detonating with uncanny precision. One destroyer captain described it simply: the sky itself was shooting back. The success was immediate and transformative. Ships that once required dense anti-aircraft coverage could now protect entire convoys. Kill ratios soared, and losses from air attacks dropped sharply. What had started as an experimental laboratory project became one of the most decisive electronic weapons of the war. The true brilliance of the proximity fuse was not only in its science, but in its manufacturing. Turning fragile laboratory prototypes into mass-produced, battle-ready components required a scale of industrial coordination that no other nation achieved during the war. More than 200 American firms were drawn into production. RCA adapted radio assembly lines to produce ruggedized vacuum tubes. Eastman Kodak, better known for film and cameras, manufactured the ceramic insulators. Western Electric supplied precision wiring and subassemblies. Every factory worked under secrecy orders. Workers were told only that the parts were for naval equipment, never learning they were building the heart of a new weapon. Quality control became an obsession. Each fuse was effectively a small radar set that had to survive the acceleration of being fired from a gun, operate for a few seconds in flight, and then destroy itself. Every circuit, solder joint, and filament was inspected by hand. In one plant, inspectors used microscopes to examine each tube for cracks invisible to the naked eye. The cost and effort were immense, but the payoff was reliability. Once mass production began in 1943, the defect rate dropped below 5%, a remarkable achievement for wartime electronics. Secrecy surrounded every stage. Naval commanders were instructed that no intact fuse could be allowed to fall into enemy hands. If a shell failed to detonate, gunners were ordered to destroy it by fire or explosives. Even Allied nations received limited information. British scientists were given finished samples, but not the design blueprints. The risk of German or Japanese counter-engineering was deemed too great. In Germany, Allied intelligence later found documents showing that their researchers suspected the existence of such a device, but never managed to reproduce it. In the Pacific, the impact was immediate. Japanese aviators flying dive bombers or kamikazes soon found themselves facing a new form of defense. Instead of random flak bursts, explosions now traced their paths through the sky. Reports from naval task forces described how waves of attacking aircraft disintegrated under the curtain of precisely timed airbursts. The fuse effectively multiplied the killing power of every anti-aircraft gun. What once required dense formations of ships now took a fraction of the fire. In tactical terms, it restored the balance of sea power by neutralizing Japan's air advantage. On land, the Army began testing the fuse in 1944. The European front provided a new challenge: ground clutter. Shells fired over forests or cities could mistake reflections from terrain for targets. To compensate, engineers modified the circuitry to adjust sensitivity and timing. By December 1944, proximity-fused shells were issued to artillery units preparing for the Battle of the Bulge. The results astonished commanders. For the first time, artillery could detonate above enemy positions rather than upon impact. A single salvo could devastate troops hiding behind cover. German soldiers described it as if the air itself had turned against them. The fuse's effect went beyond tactics. It altered morale. American troops, once outgunned in artillery exchanges, now possessed a weapon that delivered overwhelming destructive power. Reports from the Ardennes noted German prisoners referring to the invisible artillery, unable to understand how shells exploded in the air with such precision. Commanders observed that the fuse shortened engagements and reduced ammunition expenditure. In measurable terms, artillery efficiency increased dramatically. Fewer shells achieved greater results. Behind the scenes, scientists continued refining the design. Each version became smaller, simpler, and cheaper. New production models incorporated improved arming mechanisms that activated only after a set number of rotations in flight, preventing accidental detonation near friendly lines. The same technology was adapted for naval and field guns of various calibers, extending the fuse's reach across every branch of the armed forces. By 1945, production exceeded 20 million units. American engineers knew that the fuse's effectiveness relied on one factor above all: reliability under extreme stress. Every firing cycle was a test of materials science. Tubes had to conduct current without breaking. Circuits had to remain stable despite immense vibration. The laboratories solved these problems through relentless experimentation, building the foundations of what would later become modern reliability engineering. The fuse was not simply an invention. It was a crash course in precision manufacturing under wartime pressure. The proximity fuse's secrecy remained unbroken until the war's final months. Only after Japan's surrender did the Allies release full details. By then, its influence was already visible. Anti-aircraft success rates had multiplied, convoy losses had plummeted, and the morale of both fleet and infantry units had risen sharply. The fuse had proven that miniature electronics could perform reliably under the harshest conditions, paving the way for post-war radar and missile systems. As the war reached its final phase, the proximity fuse had already proven itself indispensable. In both the Pacific and European theaters, it became a symbol of the new kind of warfare, one driven by calculation, circuitry, and rapid production rather than brute force. By 1945, it had turned anti-aircraft defense into a science of probability rather than luck. For the first time, the success of gunners depended not on guesswork, but on engineering. Field commanders reported that the fuse effectively multiplied their firepower several times over. Anti-aircraft gunners could now create dense, lethal spheres of shrapnel in the air, instead of blind barrages. Convoys that once suffered devastating losses could now cross open waters under protection. Destroyers equipped with VT ammunition covered entire formations. In tactical reports, commanders described how the weapon shifted the balance of the Pacific. Japanese pilots who once attacked with confidence now approached with hesitation. often releasing bombs too early or aborting dives entirely. Yet the fuse's influence extended beyond the battlefield. The industrial effort that produced it changed how America managed science and war. The collaboration between military commands, private industry, and academic laboratories, coordinated through the Office of Scientific Research and Development, created an innovation network unprecedented in scale. This system of centralized coordination, compartmentalized secrecy, and shared technical data became a model for the post-war military-industrial complex. From missile design to space exploration, the same methods would drive American technological leadership for decades. Germany, despite its scientific depth, failed to replicate the concept. Captured documents after the war revealed that German engineers recognized the principle, but never overcame the technical difficulties of miniaturization and ruggedization. Their electronics industry, while advanced in optics and communications, lacked the industrial flexibility of America's mass production system. Japan likewise experimented with crude versions of timed or acoustic fuses, but never achieved operational reliability. The Allies' strict control over information ensured that no functional proximity fuse was fielded by the Axis powers before the war ended. Quantitatively, the results were measurable. In naval defense, kill probabilities increased by more than 4 times compared to contact-fused shells. During the Battle of the Bulge, American artillery units using proximity rounds reported casualty ratios up to 5 times higher against German forces. In every major engagement where it was deployed, the fuse amplified existing firepower far beyond the expectations of planners. It was the most successful application of electronic engineering to combat before the atomic bomb. After 1945, its legacy continued quietly. The technology was adapted for missile warheads, air defense rockets, and later for guided bombs. Its core principle, the detection of proximity through electromagnetic reflection, remained central to modern weapon design. The fuse's miniature radar circuits inspired advances in peacetime electronics as well, from altimeters to radio navigation systems. The small, sealed vacuum tubes designed to survive artillery launch evolved into the durable components of early computers and radar arrays. But perhaps the fuse's most lasting contribution was methodological. It proved that disciplined cooperation between scientists and the armed forces could yield reliable, reproducible innovation at high speed. The Proximity Fuse project had compressed a decade of research into less than 4 years. The same logic would soon guide the Manhattan Project, the space race, and the Cold War's entire framework of technological competition. By the end of the war, American officers openly acknowledged its value. Admiral Lewis Strauss called it second only to the atomic bomb in importance. General George S. Patton went further, declaring it one of the most important developments of the entire war. These were not rhetorical tributes. Operational data showed that without the fuse, Allied losses, especially at sea, would have been significantly higher. The proximity fuse illustrated a fundamental truth about the Second World War. Victory increasingly depended on systems, not individuals. Each fuse represented a tiny intersection of physics, chemistry, metallurgy, and industrial discipline. It was not glamorous like the fighter planes it destroyed or the ships it protected, but it embodied the new logic of modern conflict: precision through engineering. When the guns finally fell silent in 1945, millions of unexploded proximity fuses lay scattered across the battlefields and oceans of the world. Most were scrapped, dismantled, or buried. Yet their legacy endured in every guided weapon that followed. From radar-guided missiles to space probes that measure planetary surfaces, the same principle, that a machine can sense its environment and act accordingly, remained at the heart of 20th century technology. The proximity fuse was, in every sense, the first step toward intelligent warfare. It did not think, but it reacted. It measured, it sensed, and it decided within milliseconds. In doing so, it transformed artillery from a blind force into an instrument of precision. It was America's first true smart weapon, conceived in secrecy, built by thousands, and proven in fire. The war had begun with soldiers aiming by instinct. It ended with machines calculating for them. The proximity fuse bridged that divide and defined the future of combat.